Good morning everybody. So, we are back with fluorescence spectroscopy again. So, in our last lecture we started our discussion with this fascinating area of magnetic field effect on radical pair recombination or maybe radical pair chemistry. So, in that particular discussion, actually we discussed the origin of this particular phenomena and what could be the possible implications of this type of observations, and also we discussed some of the models that describes how this process is taking place. So, this we started and we ended our discussion with this particularly this vector atom model for spin correlated radical pairs. As you can see in this particular diagram, that if you have a radical pair, that means a pair of spins. Okay. In that case, depending on their spin parentage, means the spin state in which this radical pair is generated. Okay. So, depending on the spin parentage, it may be a singlet state of radical pair, or it may be a triplet state containing three degenerate states, of which one is T0 here, another is T plus, and the third one is T minus. Now, this cone is basically describing, and in an external magnetic field, that is your Z is the direction of the field, then according to the quantum mechanical principle, this spin vector will precess around this Z direction. So, this is your alpha, whose projection has a positive projection on Z axis plus Z axis, and beta has got a minus projection in the negative side of Z axis. Okay. And this is typically alpha 1 beta 2 type of thing, or it may have another thing alpha 2 beta 1. So, it is a linear combination of alpha 1 beta 2 alpha 2 beta 1, of course, alpha 1 beta 2 plus alpha 2 beta 1, and here this is alpha 1 beta 2 minus alpha 2 beta 1. So, that gives you the singlet state, and in case of triplet, you see that this is beta 1 and this is beta 2. So, its spin function has beta 1 beta 2, and this has got the spin function alpha 1 and alpha 2. This is called the triplet plus, this is triplet minus, and this is T0, that is T0 T plus and T minus, and this is your singlet state. So, correlated radical pair, and it's a simplified vector atom model description. Okay. And this R1 R2 are the two radical centers. In actually, suppose initially there was a bond between R1 and R2, and when this bond is ruptured homolytically, then one unpaired electron will sit on R1 and another unpaired electron is likely to sit on R2. Then it is a 2 up spin or maybe 2 down spin. In that case, it will be a triplet state. Here it is one spin up, another spin down. So, it is a singlet state. So, you can get all these details of this thing, this description in Turo's photochemistry textbook. Now, it is a revised version you can find in the market. Okay. So, generation, now the question is, it is whenever it is the question of magnetic field effect, you need to have the generation of radical pair. So, generation of radical pair. Okay. So, it may be photochemical cleavage, photochemical cleavage means you have got say like this, say this is the bond which is there. I mean this is basically a single bond, say, and you have got one part of the molecule, another part of the molecule, and when you shine with radiation, then this bond ruptures, as a result of which maybe like this, or maybe this part will have up, this part will have also up. So, depending on this relative orientation, you can have singlet state or triplet state. So, the cleavage may be homolytic or cleavage may be heterolytic. So, homolytic means one electron is sitting on here, another electron is sitting on here. In case of heterolytic cleavage, both the electrons in this pair may go over to here, leading to an excess of negative charge on this, and this part is becoming electron deficient. That is why it acquires a partial positive charge, it acquires a partial negative charge, and it generates a radical ion pair. So, it is as a result of heterolytic cleavage. And whenever you have this radical pair, so there is maybe in some cases, suppose you excite a molecule. So, when you shine with radiation, it is getting excited. Maybe what is happening, that if you think of this sigma bond, this molecular orbital theory like this. So, if you excite with radiation, then you get in the excited state, you get like this. So, this is your S0 state, say, and say this is your S1 state. Okay. So, in this S1 state, if this cleavage is taking place, maybe it will give rise to a singlet radical pair. But suppose if it undergoes undergoes intersystem crossing to corresponding triplet state, such that it is like there is a spin flip, and then after that if there is a cleavage, then you end up to this one, this second one. Okay. Now, not only this way, not only by means of this bond cleavage, you can have other methods of generation of radical pair. It is by means of electron transfer, or maybe by means of atom transfer. Okay. For example, if we think of this atom transfer process, okay, atom transfer process, like say you start with say benzophenone. It is a very well studied molecule in spin chemistry. Okay. So, you excite with appropriate radiation, maybe around 350 nanometer radiation, then it goes to BP star in the singlet state, then maybe it undergoes spin change to triplet benzophenone. Then in this triplet state of benzophenone, because it is a triplet state, it has got more lifetime, triplet has got more lifetime. So, it snatches one hydrogen, maybe from a hydrogen donor, like say this isopropyl alcohol. Okay. So, this hydrogen is snatched. Okay. So, that one radical is created over here, another radical is BPH radical, and then this radical is created. Maybe if it is in the this is snatching in the triplet state. So, you will be having a triplet radical pair, and then this triplet radical pair will undergo different processes, some of which I already have discussed. Okay. So, this is an atom transfer mechanism, atom transfer mechanism. So, this is a hydrogen atom transfer process. Okay. There are other I mean maybe you in principle you can get radical pair by means of maybe some group transfer, or maybe say some rearrangement. In that way we can also in principle generate radical pair. So, this is one way of generating your radical pair. Another is most celebrated or maybe well studied mechanism is your this electron transfer process. Electron transfer process. Now, this electron transfer process is dependent on the fact that suppose if you think of electron transfer process which is happening maybe in solution chemistry, like say some oxidant is oxidizing some other species. Oxidizing means it is accepting electron from the other species. So, it is a case of electron transfer, and like say a typical example may be say a ferrous-ferric system, Fe2 plus to Fe3 plus system. Okay. So, this is a process of oxidation. So, while it is accepting the electron, I mean it is giving out the electron to another acceptor, it is getting oxidized. So, now this process, whether this Fe2 plus is going to get you the electron or going to give this electron to other species, it is very much dependent on the reduction potential of the systems which are interacting with each other. Okay, the more the reduction potential, the greater is the tendency to be reduced. The same principle also applies to electron transfer process, and here we are mostly interested in electron transfer process in which one of the partners is in the electronically excited state. Okay. So, electronically excited state and the other partner is in the ground state. Okay, but here you see, suppose if it is a case of electron transfer, I mean this oxidation process, so it is happening in the ground state, and also the corresponding the other species which is getting reduced is also in the ground state. But here in case of electron transfer especially, it should be called as photo-induced electron transfer. Short form is PET, photo induced electron transfer. So, what is happening in this case? In the ground state, no interaction is taking place. In the ground state, no interaction is taking place, but suddenly when you shine radiation of appropriate frequency with respect to one of these two constituents, it is not like if you shine any one of them it will do it. It is not like that. In that case you have to think of the reduction potential of the ground state species and also the reduction potential of the excited state species, and in this case whichever pair is matching best with respect to this reduction potential consideration, that process is going to happen. That means, suppose you have got a donor and you have got an acceptor, okay, which do not generally interact, okay, with each other. I mean there is no electron transfer between them, donor acceptor. So, donor is giving out this electron to the acceptor. So, what is exactly happening that no interaction, no reaction is taking place, it is not happening. But suppose the process is such that when this donor is in the ground state, but say the acceptor is in the excited state, then this reduction potential consideration says that there will be an electron transfer. Then what is going to happen is that electron is getting transferred from the donor in the ground state to the excited state acceptor, okay. And as a result of which, you know, this electron transfer is taking place. So you see what is happening, that here you shine with radiation h nu corresponding to the acceptor frequency, so that it gets you to the acceptor star, and then acceptor star maybe in the singlet state, then you have the donor. So, donor gives this electron to the maybe one electron to this acceptor, giving rise to, you know, singlet state, this donor dot plus acceptor dot minus. This is an intimate ion pair. An intimate ion pair means it is within the solvent cage, it is a correlated radical ion pair. So it will evolve with time. I mean, its spin state will evolve with time. Maybe it will move on to a triplet state, or maybe while it is in the singlet state, it will undergo, you know, back electron transfer from here to here, from this acceptor to the donor back, and giving rise to the ground state species again. Okay. So this is, you know, this is something, you know, something is generally happening, and typical example is basically, suppose you have pyrene and DMA. Okay. You excite pyrene with say 337 nanometer of radiation, giving rise to pyrene star, maybe in the singlet state, and then you have DMA giving rise to one pyrene DMA radical ion pair, which is also termed as pyrene DMA plus dot pyrene minus dot, which is called the exciplex. You can see a band in the excited, I mean band corresponding to this exciplex, and everything is happening. This electron transfer is taking place within the lifetime of pyrene, which is typically several nanoseconds. So, within several nanoseconds, this DMA is transferring the electron to pyrene, giving rise to this pyrene DMA exciplex. Now, today this is the principle, I mean, for our particular this particular class, our principal focus is pyrene DMA exciplex. Principal focus is pyrene DMA exciplex, because this exciplex has got luminescence around I mean above 500 nanometer, and it is a broad emission spectra, because broad means you know, this ground state, there is no, this is not you know, attractive, but in the excited state it has got a definitive level. So, while it is doing the back electron transfer, it is coming back to repulsive ground state, and it is giving rise to you know, a structureless emission and broad emission. Okay. Now, in general, this radical, you see that these radical partners are not bonded, but the point is you can in principle prepare a pyrene DMA linked system, that you have this pyrene, okay, and say you are now linking this with say with a linker with this dimethyl amino group NMe2. Okay, this may also be possible, that you excite with radiation, then it gets excited, then electron is getting transferred from here, and in that case your radical partners are now linked with each other, okay, by means of an aliphatic linkage. Okay. So, this may also be a possibility. Now, you see, as soon as these radicals are created, I mean this say this donor acceptor, this acceptor minus dot, this is plus dot, this is created, you can expect you know, you can expect, I mean it is within the solvent cage, you can expect this cage process, cage product. or maybe cage product means this back electron transfer leading to this donor and acceptor back, okay, and everything is happening within the intimate solvent cage. Okay. So, electron transfer, you have got this excited pyrene, then you have got this ground state DMA. So, they are coming at a certain distance, this one is transferring electron from here to here. So, that it what is happening to it, it is becoming plus dot and this is becoming minus dot, and then so the moment it is created, it is surrounded by solvent. Okay, it is surrounded by solvent means it is within the solvent cage. So, it is initially maintaining some parental overall spin, maybe it is singlet or triplet depending on its spin parentage. Okay. So, cage product may be observed, or maybe parallel processes could also be like due to thermal motion, maybe solvent, they will separate this D plus dot and this A minus dot. Solvent is basically penetrating like this because of the thermal motion and trying to separate them out. Okay. It is just doing like this, so that it is now separating. Okay. Initially you have got this D and A within, and then gradually this part of the solvent is doing some motion, so that they are now like this separating out. So, that this A minus dot is surrounded by this many solvents, and this one is surrounded by D plus dot is surrounded by this many solvents, and they are now separated a little bit, and ultimately they may separate. So, when they are separating, that means you can expect this this is as a result of diffusion. So, you can expect this escape from the cage. Cage means this initial solvent cage within which this radical pair is generated. Okay. So, that gives rise to escape product. Okay. So, fate of triplet bond in the now. So, if it is a case of singlet bond radical pair, it may undergo intersystem crossing to triplet, but fate of triplet bond radical pair. So, it is generated via ISC. Okay. So, means what is happening to this triplet bond radical pair, it is generated via ISC from this singlet excited maybe donor or maybe acceptor. Then correlated and they are correlated radical pairs. Now in that case, in case of triplet bond radical pair, now singlet triplet interconversion is taking place. Now, when this singlet to triplet interconversion, so you have got triplet radical pair and you have got singlet. So, this is singlet to triplet intersystem crossing or maybe interconversion, and there are various ways by which this singlet to triplet interconversion may take place. Okay. So, if it is S state, as I told you that you can expect cage product or recombination. Recombination means basically they will recombine. So, you have got one dot over here, another dot over here. So, now they will come close to each other, and if this one, say this one is up spin and this one is down spin, they will immediately recombine. Okay. But if they are both of up spin or both of down spin, then they will not recombine unless there is any spin flip. So, as long as there is no spin flip, what will happen that they will try to do different diffusional displacement. So, diffusional displacement means they will separate out and they will escape from this cage, initial cage, so that cage escape product you can expect. Okay, more of cage. So, free radicals will be more. So, in that case you can expect free uncorrelated radical pairs. That means spin correlation is completely lost. Think about this energy level diagram. Okay. So, so here at a larger separation, this singlet and triplet, these are energetically same. So, here beyond that they are basically like free radicals, maybe around 8 angstrom to 10 angstrom. Beyond that, it is they may be treated as this is your energy and this is your separation. separation. So, in this particular region, they are free radicals, free and of course uncorrelated. Correlated means they are maintaining a definite overall spin, and it may be that in the intermediate point maybe it may be it is a combination of singlet or triplet. It is a linear combination of these two extreme states as well, but still they may maintain a overall spin correlation, means overall spin. It may be overall singlet or it may be overall triplet. Okay. So, various coupling mechanisms that are there which are important. So, spin Hamiltonian operator, which is H, spin Hamiltonian means these two spins, there is interaction Hamiltonian. So, this is used to classify the magnetic coupling mechanism of electron spin with other magnetic moments. Other magnetic moments means maybe it may be another spin, nearby spin, or maybe nearby nuclear spin. Okay, nuclear, because nuclear spin can also lead to some magnetic field around it. So, one is Zeeman mechanism. This is external coupling of spin electron spin of the magnetic moment of an applied to the magnetic moment of an applied laboratory field. Okay, so it is called the external coupling. So, basically you have external field and you have this spin. So, as a result of this interaction with this spin with the external magnetic field, that is the magnetic moment. Okay, magnetic field means magnetic moment is there. So, as a result of which there is some splitting of energy levels that is happening. Dipole mechanism, it is internal coupling of electron spin to the magnetic moment of another's electron spin. Okay. So, dipole coupling, it is called, suppose you have got this electron spin over here and you have got another electron spin over here at certain distance. So, of course, distance is a very important factor. Suppose you have got your radical of interest over here, okay, and your radical is widely separated. So, in that case if it is a large separation, then hardly it feels any effect of this one, the second one. So, this dipole interaction, dipole mechanism, which is also I mean distance is also important over there. Then hyper fine coupling mechanism. Hyper fine coupling mechanism means it is the internal coupling of electron spin to magnetic moment of a nearby nuclear spin. Nearby nuclear spin means say if you have a magnetic nucleus over here and you have got, say, radical is centered over here. Okay, suppose this is your radical and suppose this is one magnetic nucleus. Okay. So, this magnetic nucleus is going to generate a magnetic field, and this magnetic field will interact with this electron spin, and this is all internal consideration. Internal consideration means this is coming from within the molecule, this is also from within the molecule or maybe radical partner, this is also located within the radical partner. But in case of Zeeman mechanism, your radical is here and external field is being applied. So, this is our external consideration, but in this case this is internal consideration. Okay. So, there could be spin orbit coupling mechanism. So, internal coupling of electron spin to magnetic moment due to orientational it is because of the orbital motion of the electron. So, it is spin motion and the orbital motion that are coupled to each other. Okay, because you have got spin. Okay, you have got spin, and while it is spinning like this, okay, it is doing this motion as well. Okay, so this orbital motion you can think of that as if a charge is moving in a loop. Okay. So, whenever a charge electron is a charge, so it is moving in a loop means it ought to generate a magnetic field. So, that magnetic field due to orbital motion interacts with this electron spin, I mean this spin magnetic moment. Okay. So, that gives rise to an energy term which is called the spin orbit coupling mechanism. Okay. So, these are the various coupling mechanisms which are responsible for various type of things that are happening in spin chemistry. Okay. So, coupling involving two correlated spins, you see that you have got this spin 1 and spin 2 both alpha spin, okay, and this is your another another magnetic moment, or maybe another moment due to internal field, okay, due to the internal field. So, what is happening that if these two spins are coupled, so you see that that there is no change, there is no change along this z direction, no change in the overall projection, spin projection along the z direction. But suppose if these two are now coupled, this S2, the second spin, and this internal field, if these two are coupled to each other, then if these two are coupled means they are now precessing about both of them are precessing about another direction, okay, another internal direction, so that this S2 is now over here, okay, S2 is now over here. So, this is S2 after this movement, this coupling, what is happening, this you see this black arrow because of this motion. So, initially I can show you like this, initially these two were precessing, these two S1 and S2, okay, but at some moment of time you have this another spin, okay, and if these two are coupled, then they start to precess about this axis, okay. Precess about this axis means it was initially these two blacks were initially like this. Now, after this additional precessional motion, you see now it is like this. So, in effect what you are generating, you have started from a configuration like this to a configuration like this, and this is as a result of maybe this internal field in the x direction or maybe in the y direction, okay. So, maybe in the internal field or maybe some external field as well. So, what is happening that this second precession will lead to initially it was T, it was a T state, now it is a singlet state, okay. So, again when this is precessing like this, so this black will go over to here and this white will go over to here, leading to this one. So, there is a periodic transition from this this singlet state, from this singlet state to this triplet state to the singlet state, okay. So, in the zero field this is your triplet to singlet or maybe singlet to triplet. Now the moment zero, why this is happening, because they are degenerate, but in when the field is high, then what will happen that there is a splitting of this three levels, because they will no longer remain degenerate in presence of an external field. So, in that case T plus to S or S to T plus, this intersystem crossing is blocked. So, as a result of which initially, although there were this mechanism, maybe this could be due to the internal field as well. So, this hyperfine coupling mechanism that will lead to this additional precession, this Hx Hy may be internal. If it is internal field as a result of nearby magnetic nucleus, so this will lead to this intersystem crossing or maybe singlet to triplet interconversion, but the moment it is high field, that is the moment this it is called, I mean, because of this internal field there is a broadening in this T plus, T 0 and T minus. So, when this high field is such that this splitting exceeds the hyperfine broadening, then this triplet plus to S or triplet minus to S, this intersystem crossing is stopped. So, singlet triplet interconversion is reduced considerably, about 2/3 of this interconversion percentage is low, I mean is reduced. Okay. So, this is T 0 to S transition, you see, like because of this motion you see that initially it was like this. If there is a motion like this, then along the z axis h z, if it is in the z direction. So, this white is coming over here and this S is going over to there, giving rise to another, I mean initially it was T 0, now it is singlet state. Now, the physical idea is that you need to have, while there is a transition from singlet, I mean triplet to singlet, you need to have have a flipping of spin. That means this, or I mean this electron spin must be flipped. So, this flipping of electron, I mean from up spin to down spin, that must be that must be obtained from some other force, I mean from some other source. So, that is provided by your external field. That means, this conservation of this total angular momentum must be there. So, although apparently this total angular momentum has not been conserved over here, you see that there is a triplet to singlet transition, means orbital angle, I mean this total spin is not conserved, but because of this external field, whatever changes that occurred over here is compensated as a result of this external field. So, external field application, because as a result of this external field, this second precession is starting. Okay, initially they were precessing about some other direction, but the moment you are applying some external field, the spins are precessing about it. So, second precession is basically compensating for this orbital angular momentum change. So, in this case, in zero field, all three triplet sublevels are taking part in this process, but in high field only T 0 to S or S to T 0 is taking part, and T plus and T 0, these two are widely separated. So, they are not being able to take part into it. Okay. Now, think about another case, I mean think about this this triplet surface and singlet surface. Whenever it is the case of this radical pair or radical ion pair, it is the case of radical ion pair like this pyridium hexaplex. You see that this is the triplet surface, this is the singlet surface, and you started maybe the system has started maybe here in this triplet surface. So, what will happen with time? Their separation will increase, okay, and at some point you see from here to here you need to have some energy. I mean there is some energy requirement. They are energetically different. So, that is why it is always good to have good for the system to follow this path. You see that in this triplet surface, this ball has two options. One option is just to go on like this, and ultimately it will go somewhere over here to generate this free radicals, or maybe another option is there that it may go to the singlet surface. So, in that case what is happening, the moment it is going to the singlet surface, it will follow this path, and ultimately in the singlet state they are going to recombine. So, what is happening that here you have got this bond. Now, this is your geminate radical pair. You see that this maybe this is plus and minus. So, or plus and minus. So, they are separated. This is solvent separated geminate radical pair. Still this there is in I mean some of the solvent molecules have entered into it, but still it is maintaining this geminate nature, geminate radical pair may be somewhere over here, okay, somewhere over here, and then ultimately around this separation where there is no energy separate, I mean these two levels are same, then you know you can get free radicals. You see that this one is this blue one, this one is red one, they are widely separated. So, potential energy diagram for the spin and molecular dynamic features of the dynamic of a dynamic radical pair. Dynamic radical pair in the sense that they are changing their spin states from triplet to singlet or singlet to triplet depending on the situation. Okay. So, this is something very very interesting, and you see that here unlike your molecular energy level, you see that here there is a chance of singlet to triplet transition, and as a result of this spin evolution, this is called your spin evolution, that is from the triplet surface while it is moving to the singlet surface, there is a spin evolution, and there are various mechanisms by which the spin singlet to triplets ISC may occur, which I already have described over here. Okay. So, ISC of ISC, I mean intersystem crossing in the geminate radical pair in 0 external magnetic field. You see in the triplet plus state, T plus state, you see they were like this. So, that means they are contact radical pair. Okay. Here it is the bonding separation. Now, it is the stretched bonding, I mean bond is a little bit stretched, and the moment it is generated, it may be generated say in the triplet state and in the contact form, contact radical pair. So, then with time it evolves, still maintaining this triplet correlation, but there is a separation between these two radicals. Okay. Triplet correlation means their overall spin is still triplet, although there may be a linear combination of the pure singlet and pure triplet, but the overall is the triplet multiplicity, and here at some separation point, maybe here where these two are energetically almost same, there is a transition. I mean transition means you see that separation is maintained same, but only this funnel is just inverted, and this inversion of funnel means inversion of spin is taking, I mean is possible because of this this secondary precessional motion that is set in as a result of your external magnetic field, I mean around which, or external magnetic field, or maybe it may also be due to internal magnetic field, as I am telling you that it is the 0 external magnetic field. So, internal field may be responsible also, I mean in presence of an internal field, say this one starts another precession about that field direction, I mean that internal field direction, such that this funnel, this up funnel is now becoming this down funnel. So, up funnel to down funnel means you know this transition from triplet to singlet. So, I mean there in this way there is a conservation of spin, I mean you need to consider the initial state and the final state spin, okay, to find out whether there is a conservation of spin there or not. But if you think of only this one, apparently there is no conservation, but this change of spin must be compensated at some other point of the system, and then it will evolve, and then it will form this contact radical ion pair, and ultimately it will give rise to your bonding. Okay. So, here it is almost 2 angstrom, it is almost 4 angstrom, it is 8 angstrom, and free radical is about 10 angstrom separation. Okay. And this is a typical you know schematic of this radical pair for you know this exciplex case. Okay. So, you see that you have got this D plus A minus in the singlet state, then okay, then this is your intersystem crossing giving rise to triplet D plus A minus, and maybe it is giving rise to doublet D plus and doublet A minus, means it is your free radicals. Free radical means there is no spin correlation with respect to singlet or triplet, that is overall spin is not due to both of them, but it is overall spin as a result due to this one is 2 and due to this one is also 2. So, it is a doublet state, this is also a doublet state free radical. So, from singlet DA pair you can in principle get this doublet 2D plus 2A minus, and also from triplet you can get this. So, you see that this one is giving rise to recombination, and this one is giving rise to escape. Now, the point is escape means escape from cage, and recombination means recombination within the same solvent cage, okay. Or maybe in some cases there is back electron transfer. Now, the point is this whenever there is recombination means electron is getting back to this D plus, okay. So, as a result of which what is happening, that you get some fluorescence. So, this is actually expressed over here, that you have this A star excited A, as I told you that in case of exciplex A star, and so acceptor in the excited state, and you have got donor in the ground state. So, this is giving rise to acceptor minus D plus, okay, acceptor minus D plus in the singlet state, or maybe it may be in the triplet state as well, but maybe acceptor minus D plus, okay, it has got a subscript of S primed, and also it is acceptor minus D plus, it has got a subscript of S. The point is S means it is with one solvent configuration, that is a particular solvent configuration in which, or particular solvent cage containing a particular solvent configuration in which this A minus D plus is situated, and here it is another solvent configuration. So, in principle these two are different sub levels of this exciplex, okay. So, from this ultimately it is a multi-state model, and ultimately giving rise to this one is giving rise to solvent separated radical ion pair, that is A minus, it is a little separated in solvent, it is in one solvent configuration, this is another solvent configuration, and ultimately what is happening that it gives rise to completely separated radicals, of which one is minus, another is plus, okay. So, completely separated radical ions, okay. It is not radical ion pair because this is the radical pair, but these are the free radicals, okay. So, in this state this A minus D plus, this intimate ion pair, this is there may be fluorescence as also non-radiative processes, but here there will be back electron transfer giving rise to A and D, both neutral. So, the point is as soon as you have this radical ion pair, you have this contact ion pair. This is called your contact ion pair, this contact ion pair, and this is your solvent separated radical ion pair. So, this in the solvent separated radical ion pair there will be back electron transfer giving rise to this one, and here you can get this A minus D plus, this you can get fluorescence and non-radiative processes. So, what is happening that what does magnetic field do? Magnetic field, maybe if it is in the singlet state suppose, or maybe suppose if this is this is separated. So, if you apply magnetic field over here, okay, then this, if it is in the triplet state, then triplet sublevels will be separated, and therefore, singlet to triplet intersystem crossing will be reduced. So, therefore, most of the radical pairs, I mean 2/3 of the radical pair will remain in the triplet level, and as a result of which they will just escape from the cage, giving rise to escape product. But suppose if it is in the singlet state, okay, this solvent separated radical ion pair is in the singlet state. So, what will happen if you apply this in absence of any external magnetic field, in absence of any external magnetic field, what is happening, that there is a transition from singlet to triplet, I mean all the sublevels of triplet, and therefore, there is a possibility that that some of the triplet radical pairs will tend to escape, giving rise to escape product. So, you can miss some of the exciplex fluorescence because of its transition to the triplet state, but the moment when you block this singlet to triplet channel by applying this external magnetic field, then most of the radical ion pairs in the solvent separated form will remain in this singlet level, and then back electron transfer in the singlet state may lead to increased, I mean it will remain in this state, and ultimately it will go back to this state, giving rise to fluorescence. So, fluorescence will be enhanced in case of singlet bond radical pair, but if it is a triplet bond radical pair, the opposite will take place, because its initial spin parentage is triplet. So, it starts from distribution in I mean triplet manifold like T02 plus T minus, and after spin evolution it moves to singlet, and then from singlet it will fluoresce. But if it is starting point is singlet, then they have more option to fluoresce rather than go to the triplet. But and also if you apply external magnetic field in between singlet and triplet, then triplet 2/3 of the triplet is switched off. So, only 1/3 of the triplet is still connecting with singlet. So, therefore, what is happening, that your exciplex fluorescence will be enhanced in presence of an external magnetic field. Okay. So, this type of study is very important with respect to diagnostics relating to various radical induced processes, and actually if you can do some chemical reaction in a solvent cage, because solvent cage is very important, because if you have a solvent cage, I mean a cage like micelle, and if you micelle means it is a boundary. So, you do not allow radicals to escape from the boundary, and if this boundary size is such that it can make a round trip excursion, I mean going to this this region and then coming back to here. So, it is called the round trip excursion. Then what is happening, that this cage product is going to increase, because you are now caging your basically caging your radical partners. So, you are allowing the the geometry recombination to become more probable. So, as a result of which cage product will be increased in opposition to your escape product. So, basically this spin chemistry is a fascinating area where you can explore many things that is happening in chemical systems, especially involving radical pairs, and how an external magnetic field can affect this process. That I guess that this concise discussion might have given you some idea of what is exactly happening. So, if you want to know details of it, you can consider this, you can read Toureau's textbook, and maybe if you search literature, then in many journals you will be finding many articles which describe various phenomena, chemical phenomena, where this magnetic field has got a paramount role in controlling the overall dynamics of the of spin recombination. So, that is all for today. Thank you.